Welcome back everyone. In this lecture I am going to prove the Frobenius reciprocity law. So, first let us work with the characters and then recall what happens to the restriction representation and induced representation. So, as before let us fix some notation. So, we take G to be a finite group and H is G's subgroup. So, now if we take some function f from G to C, then we can talk about the restriction of the function to H. So, given f which is a function whose complex valued function from G. So, that means f is a function from G to C. So, for this function we can talk about the restriction f restricted to H, which is again a function from H to C. So, now because we are going to use this restriction as RESGH, so we are going to use the same notation for these functions as well. So, we are going to denote this restriction of f from G to H as this RESGH f. So, which is exactly f restricted to H. So, this is the notation. So, now what we are going to do, we want to actually restrict our attention to the characters, but characters are the class functions. So, maybe we can actually just restrict to the class functions and then see how this restriction is actually behaved. So, here is the proportion which is easy to verify. So, let me state it. So, as before let us fix H being a subgroup of G. So, then we have this restriction function from G to H, which is a map from this the space of class functions C G to the space of class function on H C H, and this is indeed a linear map. So, this is a linear map. So, let us not worry about the other structures that we have it on these spaces. So, we will just verify that this is a linear map. That is good enough for us right now. So, basically what we need to verify, if we take a class function f from this z of C G, then the image of that f, that means the restriction of that function to H is again a class function, which is indeed one line proof. So, let f from this space of class function. So, recall that this is the space of class functions. So, then what we know that f of x h x inverse equal to f of h for all x h in G. So, this is satisfied. So, now let us look at the restriction. So, what happens to the restriction? The restriction is a function from H to C. So, this is a function from H to C. So, f is a function from G to C. So, now we want to verify this is also a class function, is also a class function. So, that is our claim. So, let us just check this. So, if we just take x and h from H, then what happens? So, for h x from capital H, we have the restriction from G to H f of x h x inverse is going to be exactly equal to f of x h x inverse, which is f of h because f is a class function. So, that implies that this is exactly equal to the restriction of g h f of h. So, that means this restriction indeed belongs to this z of c h. Okay. So, this is just simple proof. So, now the linearity is also immediate. Let us actually look at the linearity. So, if you take f1 F2 from z of Cg and then C1, C2 from the complex numbers. So, then what we have, we take this restriction GH of C1 F1 plus C2 F2. So, this is going to be exactly equal to, so when you apply it on some H for H in H, so we have this is exactly equal to C1 F1 of H plus C2 F2 of H. So, that is going to be exactly the definition of C1 times the restriction of G2H F1 of H plus C2 the restriction of GH F2 of H. So, that means we have the linearity for all H in H. So, that would imply that this function C1 F1 plus C2 F2 is exactly equal to C1 times the restriction of GH F1 plus C2 the restriction of GH F2. Okay, so, this actually proves the proportion. Like I said, it is very simple exercise to prove this. So, now let us look at this opposite map. So, the opposite map is indeed given by the induction. So, our ultimate goal to construct actually the inverse map in some sense. So, what is that map? So, let us say we want to construct a linear map now from the space of class functions on H to the space of class function on G. So, this is what we are interested in. So, let us actually do that at the level of functions, then it will be clear like how the character of the induction will naturally appear here. So, if H is a subgroup of G, then F is a function from H to C. So, then it is easy to associate a function F dot from G to C. So, by declaring like so extending that function trivially to entire G. So, let us start with this function F from CH. So, now that means F is a function from H to C. So, now what I can do, so we denote this F dot which is a function from G to C. So, this is extension of F trivially to all of G. So, what is the meaning of that? That means F dot of x is going to be exactly f of x if x comes from H and it takes the value 0 otherwise. Okay. So, this is the what we call trivial extension of f to f dot, and we have this map from f to this f dot where from G H to C G, and this is easy to define. Now, we want a map from the space of class function to the space of class functions. So, for that purpose we need to actually kind of need to be little bit careful, because it is clear that the trivial extension f dot is not going to be a class function if you start with class function f. So, we have to kind of really modify the definition. So, this is where actually the induction comes into the play. So, now if we start with a function f from let us say from z of ch, then it is a class function. That means f of x h x inverse is going to be equal to f of h for all h and x in capital H. So, this is satisfied. So, what we want a function from G to C, and which is actually extending this f, and it is actually going to be a class function again. So, if we take this f dot, it is clear that this is not a class function. So, somehow we need to modify the definition of this f dot. So, how do you modify? So, we just use what is this called this induction. So, this induction of f from H to G. So, that is defined to be. So, if you go back to our proof of the character, so you can see that the induced character satisfies this particular equality. So, the induced representation character is given by 1 divided by the cardinality of H sum over this character of this H representation W applied on x g x inverse, where x runs over G such that x g x inverse is in H. And this is the expression that actually kind of we are going to take it for the induction of any class function. So, motivated from that, it is clear that we can define this induction of this function f from H to G as follows. You take 1 divided by the cardinality of H, where you sum it over all x in G. Now, the data that x inverse G H supposed to be in H, that will be stored in the f dot. So, you take simply f dot of x inverse G x. So, this is the function when you evaluate it on G in G. So, this is how for any G in G. So, you define this function as follows. So, this is the function that we are talking about. So, note that this f dot is a function that takes value f of x if x is in H and 0 otherwise. So, that kind of this thing takes care of whether x inverse G x is in H or not. So, that is what was there before in this formula, where we demand this x g x inverse as an element of capital H. So, that is actually satisfied, taken care of by this f dot. Now, we have defined this induction. So, now given character chi of H, then we have naturally this induced character of chi. So, given chi, which is character of this capital H, so then we have this induced character chi, which is a character on capital G. Okay. And if you start with the representation, then the induction that we have defined has the character which is this induction of this chi. So, that is already we proved. So, now what kind of map is this induction map? This is as we expected, it is going to be a linear map from the space of class function to the space of class function. So, maybe I will state it as a proportion. So, again take H to be a subgroup of G. So, then the map, the induction map that we defined. So, this induction map, which is a map from the space of class function on H to the space of class function on G, where f is mapped to this induction G H F, and this is indeed a linear map. So, this is the opposite map that we were actually looking for. The restriction is easy to define, but this induction takes some time effort to define. But anyway, it is naturally defined using the induction of the representation. So, now first we need to verify that this induction is indeed really a class function, and then the linearity also preserved. The linearity is actually simple check, maybe let us do that first. So, if I take f1 f2 from this the space of class functions, and then c1 c2 from the complex numbers. So, then if you look at this in G H c1 f1 plus c2 f2, and you evaluate on G, where G in coming from capital G. So, then we have this is exactly equal to 1 divided by the cardinality of G summation, where x in G c1 f1 plus c2 f2, where we take dot of this, and then you apply x inverse g x. Now note that the dot is indeed linear, that we have already verified. So that means this can be split into the linear combination, and that is going to give us exactly equal to 1 divided by the cardinality of H summation x in G. So we can take this C1 out, and F1 dot of x inverse Gx plus C2 out, and then 1 divided by the cardinality of H summation x in G F2 dot of x inverse Gx. And this is the definition of induction of F1, and this is the definition of induction of F2. So that tells you that this is exactly equal to C1 the induction GH F1 plus C2 the induction GH F2 of G. Okay, so this verifies the linearity, that is something easy to verify. So now let us look at why this maps class function to class function. So let us start with f being a class function. So it is a class function on capital H. So we have that f of x h x inverse is equal to f of h for all x h comes from capital H. So now you have this induction applied on f, and if you recall the definition, when you apply it on G, so then you get exactly 1 divided by the cardinality of H summation Z in G f dot of Z inverse G Z. So this is what we get. So this is by definition. So now let's compute what happens to induction GH f of y inverse GY. So where G, Y, they are all coming from capital G. Okay. So then this is going to be exactly equal to 1 divided by the cardinality of H summation let us say x in G f dot of x inverse y inverse G y x. So this is what we get. So now we can simply use this change of variable. So if you denote yx to be z, then z inverse is going to be x inverse y inverse. So then this you can rewrite as 1 divided by the cardinality of H summation z in G f dot z inverse G z, which is exactly equal to the induction of f at G. So this verifies that the induction of f is again a class function. So that means the induction defines a linear map from the space of class function to the space of class function. So now we are going to state this Frobenius reciprocity theorem. So that actually asserts that the linear maps, restriction and induction, they are adjoint. So basically we are going to state the result in terms of the inner product. So I am not going to explain as a functor what they mean by adjoint. So let us actually simplify our life, and then I will just write down what they mean in terms of the class functions. So in practice it says that if chi is an irreducible character of G and theta is an irreducible character of H, then the multiplicity of chi in the induced character induction of theta is exactly the same as the multiplicity of theta in the restriction of chi. So that is what Frobenius reciprocity actually tells us. So let us actually write down explicitly what I meant by that statement. So here is the theorem. So this is proved by Frobenius. So, what this theorem actually states, so again fix this H being a subgroup of G, and now what we are going to do, we are going to state the theorem even for some class functions. You take A to be a class function in ZCH and B to be a class function in ZCG. Okay. So, then we have the formula that reads as follows. If you take the inner product of the induction of A from H to G, and then if you compute the inner product between this induction and B, which is same as computing the inner product between A and the restriction of G to H on B. Okay. So, this is how the formula is written. So, like I said, if you start with an irreducible character of G, so let us say chi is irreducible character of G and theta is irreducible character of H. So, then we are interested in the multiplicity of chi in the induced character of induction of theta. So, this induction theta. So, you are interested in the multiplicity. So, we all know that the multiplicity of this captured by this inner product, and we are saying that this is exactly equal to same as the multiplicity of theta inside the restriction of G to H in chi. Okay. So, now note that so this one is like these two are indeed representations of G and these two are representations of H. So, somehow the reciprocity actually connects the induction with restriction via this equation. So, this is what it means when it comes to representations, and this is this statement is immediate from this statement. So, we are going to verify this statement that I have written here. Let us call it star. So, this is now just a direct computation, and so this is actually kind of follows from the fact that the induction of theta is just given by the induction applied on this theta. Okay. So, let us verify this. Let us start with the left hand side. So, what it is, we are going to compute the inner product between the induction of A and B. So, by definition the inner product is given by 1 divided by the cardinality of G summation over G in G, the induction of A of G and then B of G bar. So, this is the definition of the inner product. So, now if you just rewrite the definition of this induction, then what we get? We get exactly 1 divided by the cardinality of G summation G in G. Now, 1 divided by cardinality of H summation x in G. So, now you get this A dot of x inverse G x. So, this is what you get. So, this term is exactly this term and times you have this B of G bar. So, now if you just take out all these denominators, 1 divided by cardinality of G times 1 divided by cardinality of H and the group the terms. So, we can actually switch the sum. So, then you get x in G, G in G. So, then you get this A dot x inverse G x times B of G bar. So, this is what the left hand side looks like. So, now let us actually recall the function a dot, what it means. So, a dot is going to be 0 whenever this x inverse g x is not an element of H, and whenever it is so it is equal to a of x inverse g x only when x inverse g x is an element of H. So, that means we can rewrite the sum as follows. So, whenever this x inverse g x, if it is H and that is an element of capital H, so then this a dot of x inverse g x looks like exactly a h. If we do this substitution, then LHS becomes exactly equal to 1 divided by the cardinality of G, 1 divided by the cardinality of H, summation. Now, sum runs over G in G and now H in H, because all other terms will be 0, A of H times B of now H x x H x inverse. So, that is what we get. So, this is because once you substitute H equal to x inverse G x, then G will be x H x inverse. So, from here you get G equal to x H x inverse. That is the substitution we have done. Now, note that B is indeed a class function on G. So, B is coming from Z of C G. Since it is a class function, so this value indeed is equal to B of H bar. So, we can substitute that there. So, then we get this is equal to 1 divided by the cardinality of G, 1 divided by the cardinality of H, summation x in G and then H in H. You get A of H times B of H bar. So, this is what you get, but note that this summation H in H, A of H, B of H bar is nothing but the inner product between A and the restriction of B. So, this is 1 divided by the cardinality of H. So, this is exactly equal to the inner product between A comma the restriction of G to H of B. Okay. So, that is something I can substitute here. So, then the left hand side becomes exactly equal to 1 divided by the cardinality of G summation x in G, the inner product A comma the restriction of G H B. Now, since there are exactly cardinality of G elements, so this is exactly adds up to A inner product A comma the restriction of G H B. So, this is what we wanted to prove. So, we wanted to prove that if you take induction of A comma B, the inner product which is same as A comma the restriction of G to H B. Okay. So, this actually proves. So, now if you just specialize to the class functions which are characters, so then we get what we promised before. Okay. So, I already told you that if you take for example, theta being character of H, if theta is character of H, so then this induction of theta from G to H, so this is indeed the character of the induction that we defined before, induction of G H, maybe let us say the corresponding representation is W. So, W is representation with theta as character, then the character of this induction is exactly given by the induction of this character theta. Okay. So, because of this close relationship between this induction function and then this induction of representation, so this equation can be reinterpreted in terms of the representations, and that is what we stated in the beginning. So, when you take chi is irreducible character of G, theta is irreducible character of H. So, then the multiplicity of chi in the induction of theta is same as the multiplicity of theta in the restriction of chi. So, which is somewhat very powerful connection between these representations of these respective groups G and H. Okay, so this actually completes the proof of Frobenius reciprocity. So, we can actually use this Frobenius reciprocity in order to get characterization of irreducibility of these inductions. So, it is actually not difficult to see the induction of irreducible characters need not be always actually irreducible. So, the Mackay's criterion that actually gives characterization like when it will be irreducible. So, maybe I will actually do that in the next class. I will stop here. Thanks.